Hey everyone, so today we will see fundamental theorem of calculus 1. Now there are two fundamental theorems, but today we will only concentrate on fundamental theorem of calculus, which is FTC 1. Okay, so I am not going to tell you the proof of the theorem because that's a very standard proof. What I am going to do is I will tell you the meaning of the theorem. We will try to understand the statement using examples. And then I will take 3-4 very different kind of examples, which is fun to solve. Okay, that time you will realize the importance of FTC. Okay, so what is FTC1? So before that also, why the name fundamental? What is so fundamental about this theorem? Well, it is called as a fundamental theorem of calculus because it connects two different basic and important topics of calculus. What are those two? Differentiation and integration. Now once you study the topics, you know that derivative of a function at a given point is the slope of a tangent line, and integration of a function over an interval, it gives you the area under the curve. So this is an infinite sum. So obviously at first go no one can say that there can be a connection between them, right? So they are totally different, unrelated topics. But what does this theorem do is it connects the link between the differential calculus and the integral calculus. This is the reason we call this as a fundamental theorem of calculus, because it connects two unrelated topics in a very nice way. Okay, so FTC1 talks about how does derivative of integration behaves, and FTC2 talks about how integration of derivative behaves. Some author also interchange the name, like some people call this as FTC1 and this as FTC2, but since I'm referring Thomas' book, so I will go with that convention. So I'm calling FTC1 as how derivative of integration of a function will behave. Okay, so that's what we are going to see in today's lecture. So let's try to see the statement and try to understand the statement using an example. So suppose if you have a continuous function over a closed and bounded interval AB, and you define a new function f of x. What is my capital F? You are simply finding the area under the curve from a to x. Okay, so as this is my x, this is my x. So as you keep on changing in the input, this will keep on changing upper limit. The lower limit is a constant, it's a number. Okay, so what is my capital F? It is the area under the curve y equal to f of x over the interval a to x. Okay, this is what my capital F is. Then it says that this is also continuous function. That means integration of a continuous function is continuous. Integration of a continuous function is differentiable. And when you take the derivative of capital F, that means what? So when I differentiate this both sides, so what I have, d by dx of f of x is equal to d by dx of integration a to x f of t dt. So I simply took derivative. So what is this? This is my f dash of x. The theorem says this gets cancelled and what you get is f of x. So derivative of integration is nothing but the integrand. I am cutting for your understanding purpose. Okay, so yeah, so that's what this says, that derivative of integration is integrand. Okay, so that's how you can keep in mind. What is FTC1? It talks about derivative of integration. Okay, so derivative of integration is nothing but the integrand. That's what the theorem is. Now let's try to understand this using an example. So let me take the simplest of the example. So let me take the function f of x equal to x and let me take the interval 0 to 1. So I know that it's a continuous function. My suggestion will be you just see the statement once again from the book or the Google and see the proof as well. So this is my function y equal to x. Now what I will do is I will define my capital F of x. What is that? Integration 0 to x f of t dt. So what is this integration 0 to x? What is f of t? F of t will be t dt. And what is the integration? T square by 2 0 to x. And what is this? X square by 2. So if this is my small f of x, if I integrate that, my capital F is nothing but x square by 2. And when I take the derivative of this, what is f dash of x? What is derivative of x square by 2? Is x only. It's 2x, 2 will get cancelled. So f dash of x is equal to x, which is nothing but my small f of x. So f dash is nothing but small f of x, and that's what the theorem was, right? So yeah, that's kind of one example to understand this. Now let's try to imagine that using the area thing. Okay, so what is the function? This is what you have, integration of t dt. Okay, 0 to x. So what is this function doing? So it is a function, say from 0 to 1, and it gives you the area. So when I take suppose 1 by 2, so what is f of 1 by 2? It is 0 to half. So it will, so f of 1 by 2 will give me the area under the curve over the interval 0 to half. So f of half, this is nothing but my f of 1 by 2. What will be my f of 1? Integration 0 to 1. So when I integrate 0 to 1, so this whole area is nothing but my f of 1. So f of 1 will give me area under the curve y equal to x over the interval 0 to 1. What will be f of 1 by 4? It will be integration 0 to 1 by 4. So if I take this as 1 by 4, this is what the area I get. It's like in the computer program, like if you want to write a program, so if I enter the value of x, I will get that much of the area. So when I put x equal to 1, I will get the area of this function over the interval 0 to 1. If I put x equal to 1 by 2, then I will get area under the curve y equal to x over the interval 0 to 1 by 2. Okay, so this is acting as a variable. So this is what my capital F means. So I hope you understood the capital F notion. Now, what is this f of x? It is giving me the area, right? So if x is any variable, so if suppose this is my x, till here it is x. So my base is x. What will be my height? Since this is y equal to x, my height will always be x. It's a triangle. So what is the area of this triangle? Half base into height. So what I get? Half base into height, x into x. So what is this? Half x square. And that's what we got when we integrated. So what is my function? So area of this function over the interval this is given by this function. So you keep on changing the domain, you get different area of this function. I hope this is clear. If not, you can again rewind and see what I said. So this is the area of this function. Okay, as my x will vary from 0 to 1. So as you can see, when my x is 0, what is the area? Nothing, 0. So f of 0 is 0. When my x is 1, what is the area from 0 to 1? It is 1 by 2. So as you put x equal to 1, you get 1 by 2. So area under the curve for this function is represented by a function. I hope this is a purple color I took. So I hope that is clear. This point will be 1 by 2. So at 1, the area is 1 by 2. So there is the parabola I have drawn. So purple line, purple curve represents the area function for y equal to x line. And now when I take the derivative of this f dash of x, what I get? X. So what is the derivative of this parabola? When I take the derivative of this parabola x square by 2, I get the line. So when I take the derivative of this, I again get back the line. So I started with line. I wanted to find the area. So the area function comes out to be x square by 2. And when I integrate this area function, I am again getting my function y equal to x. So derivative of integration is again the function itself. So yeah, so that's two different ways of understanding the statement. So first I directly integrated and I verified that capital F dash is small f. And here I tried to explain you using the diagram. Okay, so don't get confused. Whichever is comfortable to you, you can take that along with you. Okay, so that is FTC1. Now let's take 2-3 different examples. So first let's start with the simplest example. So what is my function? Integration 0 to x tan of t square dt. And the question is, what is y dash? What is the derivative of this function? So if you don't know FTC, what you do, you try to integrate this. But I think that is also difficult, right? Because integration of tan is log of sec, if I'm not wrong, log of sec x. but then log of sec t square into 1 upon 2t. But then again, when you're dividing by t, it is not defined at 0. So integration will be difficult, but anyways, that's the good point of FTC. If you have a function where one of the limit is constant and one of the limit is a variable of degree 1, then the derivative is nothing but integration goes away. What is the derivative of integration? It is nothing but the integrand. So my y dash is nothing but tan of x square. Okay, suppose if you have y equal to integration x to 2 and you have sine of e raised to t dt. Again, if someone has asked you y dash, so again you can see one is the constant and one is the variable. So one thing you can do is first to interchange. So when I interchange the limit, minus sign comes here. This is sine of e raised to t dt. So whenever you have integration of a function and the nice limits are there, no need to evaluate that integral if you want to find the derivative. Okay, and now if you want to find y dash, minus sign will come. What is derivative of integration? It is integrand. So sine of e raised to x, not t, okay, x. So this is the derivative. Now let do some modification. Okay, so this were quite simpler. What if the degree is not 1? Okay, so what if one of the limit is a variable but the degree is not 1? Suppose y is equal to 0 to suppose sine x into e raised to t dt, and I want to find y dash, or let me take tan of e raised to t. So okay, it's difficult to solve, so but I want to find y dash. So what I will do, I will first make this as only a linear polynomial, or I mean it should be only x, right? So what to do is you put u is equal to sine x. So what will I get? I get y is equal to integration 0 to u tan of e raised to t dt. Okay, so that's the first step, the substitution. What is the second step? Now what you want to find? You want to find dy by dx, but by chain rule, what is this? This is dy by du into du by dx. But what is d by du of y? D by du of y. What is my y? It is integration 0 to u tan of e raised to t dt into du by dx. What is u with respect to x? It is cos x. But by FTC, what is derivative of integration? It is integrand. So tan of e raised to u into cos x. So finally at the end, everything should be in terms of x. So what is my u? U is nothing but sin x. So tan of e raised to sin x into cos x. That's what my y dash is. So if one of the variable is number but other variable, if one of the limit is number and another limit is not x, it is something a function of x, then do the substitution, apply chain rule, you get the answer. And I don't know whether you have seen a formula. Actually this gives you a very nice formula. So if you have, so if this is some f of x, okay, then what you see here, tan e raised to f of x into what is this? Derivative of f of x. So this is what the formula is. So if you have something like this, then y dash is nothing but, suppose if this is my some function, say g of t. So what you are doing, wherever you had t, you replace your t by the upper limit. So y dash is nothing but g of f of x into f dash of x. So this is the formula if the upper limit is not x, is some function of x. So what is the derivative of the integration? G of, wherever you have t, you replace your t by f of x into f dash of x. Okay, so if someone now in the competitive exam, if you come across this question, suppose y is integration 0 to tan x e raised to t dt. So what is my y dash? Here wherever you have t, you replace your t by f of x. So e raised to tan x into derivative. What is derivative of tan? Sec square of x. So see, it becomes very easy. So if you don't remember this formula, earlier what I wrote by chain rule. Make sure that part is clear, okay? Because this is a formula, but there's a general technique or algorithm that one should know. Okay, so now let's end this session with a very nice example. Okay, so you have to investigate the maxima and minima for this function. Now function is integration. So what is f of x or y of x? 1 to x of this function. Now don't even think of solving this integral. Okay, it will take a lot of time. So what to do? So since to find maximum minima, what I want? Okay, before that, is the domain given? No. So what do you take the domain as? Whole real number, minus infinity to infinity. Okay, that's one thing. So we know the domain. For maximum minima, what we want? We want the critical points and the endpoints. There are no endpoints because I'm taking whole real number into the domain. So what are the critical points? So you take the derivative equal to 0. So what is derivative of integration? One limit is constant, another limit is x. So derivative of integration is the integrand. So 2 into x minus 1, x minus 2 cube plus 3 into x minus 1 square, x minus 2 square. Now what is this? This is, you take out x minus 1 into x minus 2 square outside. What is left? 2 times x minus 2 plus 3 times x minus 1. This is x minus 1, x minus 2 square, 2x plus 3x, 5x minus 4 minus 3 minus 7. So this is what my y dash. See, so there's the power of FTC, fundamental theorem. If you don't know that theorem, what you would have done? You would have evaluated that integral and then you would have taken the derivative. But see, here in 3 lines you get the derivative. So there's the power of FTC. Okay, good. Now what are the critical points when this is 0? Now when this is 0, so your x is either 1, 2 and 7 by 5. So these are my critical points. There are no endpoints. Good. So to find maximum minima, you draw the interval, the first derivative test. So I have interval minus infinity to 1, 1 to 2 and 2 to 7 by 5 and 1 to 7 by 5 and then 7 by 5 to 2 and the last is 2 to infinity. Correct? That's what the table is. Then you look for the sign of f dash and then you say whether the function is increasing or decreasing. Okay, so this is my f dash. Now in this you take suppose 0 because 0 is in this interval minus infinity to 1. So what is the sign of f dash? When I take 0, this is negative, this is square, so this is always positive, this is negative, so negative is positive. From 1 to 7.5, 7 by 5, what is 7 by 5? 1.4. So if I take 1.1, 1.1 is in this interval, so this is positive. When I replace x by 1.1, positive, positive, negative. Okay, then if I take 1.9, if it is that in the second last interval 1.9, positive, positive, positive. And if I take 3, so positive, positive, positive. So as you can see, it is increasing, decreasing, increasing, increasing. So as f dash is changing the sign at 1 and it is changing the sign at 7 by 5. So at 1, f dash is changing from positive to negative. So at x equal to 1, you have maximum value. And at 7.7 by 5, f dash is changing the sign from negative to positive. So it has a local maxima at x equal to 1 and it has a local minima at x equal to 7 by 5. And now if you want to find the value, what is y of 1 at x equal to 1? What is the integration? 1 to 1, right? Because x is 1. So whatever this dt, so this answer is 0. So the maximum, the maximum value is 0. And what you need to find? Y of 7 by 5, which is integration 0 to 7 by 5 dt. Doesn't matter, I don't want this value actually. I only wanted to see at where the maxima or the minima occur, if they exist. So yes, so answer is local maxima occur at x equal to 1 and the local minima occur at x equal to 7 by 5. So isn't this a nice example? So yeah, that's the strong point of FTC. So now let me give you one homework problem. So here are two homework problems. First you have to tell me what is y dash. So in the first example, tell me y dash in the comment section. And for the second question, you have to tell me the points where this function has local minima. So find the derivative, draw the table, see where the sign is changing. You can take complete real number as the domain for this. X is from minus infinity to infinity. So tell me the points of local minima. So that's all about FTC1. So I hope this is clear to you. If yes, then do not forget to like, share and subscribe. If no, then definitely you must be having some doubt. Then you can ask me that doubt in the comment section. Thank you.